Today on Macaulay Math, we're talking the law of sines. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 29 on the law of sines. Our goals for today. We're going to use the law of sines to solve oblique triangles. We're going to find areas of oblique triangles, and we're going to use the law of sines to solve problems. The last unit focused on the algebra of trigonometry and how to manipulate trigonometric functions. This unit returns to more concrete applications for trigonometry. Most importantly, this unit discusses the law of sines and cosines, both of which deal with oblique or non-right triangles. Both the law of sines and cosines have real-world applications. Both are simple formulas that have well-defined uses. The law of sines has an issue of ambiguity, which makes it a bit more difficult to understand. So we will start with that one first. Let's get started.
Okay, let's start with this definition of the law of sines. And the law of sines is an extended proportion in which all three, but you will only ever use two of the ratios in a proportion at any given time. So I will never use all three. I'll just use like the sine of A over A equals the sine of B over B. The law of sines has certain situations in which it works best. And the way it works best is when you are given two angles and an excluded side. So as a for instance, if you were given angle A, angle C, and side little a, so the two angles that are adjacent to each other with a side that is excluded. Another good use for the law of sines is when you have two angles and an included side. So if I had, say, angle A, angle C, and the side that's in between them B, that would be a situation when you had angle, side, angle. It works, but is not so great for side, side, angle. So if I'm given, say, side B and side A and then angle B, two sides and an excluded angle, that will work, but this is the ambiguous case. You have to do a little bit more work, check to make sure that there's only one solution for that. Now, the configurations that cannot be used using the law of sines is if you're given three sides, so if you're given little a, little b, and little c, or if you're given side angle side, so two sides, say side A and side B with the included angle C. You must use the law of cosines, and we will address that in the next lesson. All right, let's solve an oblique triangle, and in this particular case, let's do one where we are using the strong forms. And if you look what I'm given two angles with an included side. So that is one of the strong ones. That is the angle side angle configuration. And so what we'll do is we'll just make a list here. So we will go angle A, angle B, and angle C, and we'll put equals on all of these. And then we'll go side little a, side little b, side little c. And when we fill in all of these blanks, we will be done. Now, we're given some of these things already to start. Angle A is 32 degrees, 32. Little c is 46 degrees, so we'll put 46 degrees there, and we'll have that calculated. Angle B, we don't know, but we're going to calculate that fairly quickly here. That'll be the first thing that we do. But we do know what side little b is, and that is just going to be 10. And in this case, since they give it the units of meters, we will add meters. So we need to solve all of these parts. Now, before we get started, I want to say that I know that this is the law of sines, but especially for this lesson and the next lesson, law of cosine, you are allowed to use all of the methods that you have learned up to this point. Sometimes you are going to be forced to use the law of sines, but if you can use a simpler method, go ahead and do that. And I'm going to illustrate that by solving for angle B first, not using the law of sines, but using the triangle sum theorem. And the triangle sum theorem states that the sum of all of the angles in a triangle have to be equal to 180 degrees. So if I were in this case to go angle A plus angle B plus angle C is equal to 180 degrees, that is a true statement. So I can replace this A with 32 degrees. I don't know what angle B is. I can replace angle C with 46 degrees. Has to be equal to 180 degrees. And so 32 degrees and 46 degrees is 78 degrees plus angle B, still equal to 180 degrees. And so if I subtract away 78 from both sides, I get angle B being equal to 102 degrees. So we'll go back up here to the top. We'll put 102 degrees there, and now we have all of our angle measures. All right, now to find the remaining two sides, little a and little b, we are going to use the law of sines. Now, the way that you use the law of sines is you have to know a side and an angle, and then you can use one other piece of information in the given to find its opposite part, so either an angle or a side. Now, in this case, I know angle B and the length of two steps because I can't solve for all three at the same time, but the method will be the same. So here, let's solve for little a first. I know that the sine of 102, that first angle, over the side opposite of that, which will be 10, that is my known proportion, will be equal to, I'm solving for little a, I know that its opposite angle is 32, is equal to the sine of 32 degrees all over little a. Since this is a proportion and we can calculate the sine of 102 and the sine of 32, we can cross multiply and divide. And so if I cross multiply, I'll have a times the sine of 102 degrees is equal to 10 times the sine of 32 degrees. And then I'll divide both sides by the sine of 102. That'll give me little a is equal to 10 times the sine of 32 degrees all over the sine of 102 degrees. And that we can calculate. So we're just going to put that into decimals. We are in decimals, but let's make sure we have the correct settings. So let's go over here to the wrench and make sure we are in degree mode, because that is the units of measure that they are given for the angles. And now let's put this in the calculator, and we'll put parentheses around the top. We'll go 10 times the sine of 32 degrees. And we want to divide that by the sine of 102 degrees. That gives us 5.4175. So if we're rounded to three places for our final answer, this 5 is going to round that 7 up to an 8. And that will give me 5.418. And again, we're talking meters. So I'll go back up here. 5.418 meters. And we're going to do the same thing, but we're going to solve for little c here. So again, I know the two parts for angle B and little b. I'll have the sine of 102 degrees over 10 meters is equal to the sine of little angle C, which we know to be 46 degrees all over little c. And again, cross multiplying and divide. We've already done this once, so we'll just go c will be equal to 10 sine 46 over the sine of 102. And we can just go right back to Desmos, and all we'll have to do in Desmos, since this is almost the same, all I have to do is change that value there. Instead of 32, I'm going to type in 46. and they give me 7.354. So we're going to leave that as a 4 since the rounding value would be 1. So C is equal to 7.354, and again meters, 7.354 meters. And since I have all 6 of the values now, we are finished. Okay, next issue that we have to talk about is the side angle ambiguous case. Since sine is positive in both the first and second quadrants, there is the possibility that certain oblique triangles that have side angle arrangement may have 1, 2, or no solutions. And so what I mean by that is if I use this diagram here to kind of picture the unit circle, and I make this angle here, let's say I make it 60 degrees, and I come over here and I make this angle here 120 degrees. Since they mark off the same value, the sine of 60 degrees and the sine of 120 degrees, we know that those are the same value. They both have a value of square root of 3 over 2. Therefore, I could make 2 triangles, one with a 60-degree angle and one with a 120-degree angle, that could have the same lengths for 2 of the 3 sides. And so what we come up with, so we have an opportunity where we could have a situation where you have 2 possible correct angles. And here is a side angle configuration. And in this case, there is the possibility of 2 triangles that work with these 3 given pieces of information. Now that's only going to happen when the height of the triangle is smaller than the opposite side of the given angle, which is smaller than the side that is adjacent to the given angle. And if you think about it, if I don't change A, I could take this triangle here and I could sweep this side down and not change anything, and this side here still be equal to the A in the original position, and I have 2 different triangles, one here and then one there. Additionally, there is an opportunity where you could have 0 triangles. Here is a situation where I have side angle again. If A is obtuse, then we're only going to have 1 triangle. But if A were to be shorter than B, let's just say as a for instance, we made A shorter than B, it's too short to touch that side. So if A is shorter than B, I have no triangle. And so what I've done is I've made a little chart for you to look at. And here is the chart. If you take that configuration where you're given angle A, side little a, and side little b. So we have it set up to fit this. If you have an acute angle for angle A, if A is less than H, is less than the height, you'll have no triangle. And that's easy to show. If A is shorter than H, it's too short for it to ever even hit the third side. So A has to be bigger than H for you to have a triangle. If A is equal to H, then you have 1 triangle, and it is that right triangle because H is an altitude, and altitude is defined by perpendicular sides. If you have an acute angle A, side A is bigger than side B, then you're only going to have 1 triangle. And we've shown the way that you can have 2 triangles. If A is obtuse and A is smaller than B, then you have no triangle, and I showed that. And if A is obtuse and A is bigger than B, then you have 1 triangle. I'm not going to say that you have to memorize this, but you do have to know what situation is which. So to determine an ambiguous case, draw your diagram and then find the length of H. Compare A, B, and H, and then to decide which instant applies based on that table, and then make a decision based on 4, and then you're going to solve. So here I am doing an example where I absolutely know in advance that I am going to have two triangles, and I want to show you how to go about doing that. So here I have A, I have C, I have B up here, and this is going to be an instance where we have two solutions to this. And again, I want to figure out both of them. So the first thing that I want to do is I want to find the length of this H right here. All right, now, since the H is an altitude, I know that it has to be a right angle here. That makes this a right triangle. And I can calculate H because I know I have a 60-degree angle here. This side is 10. I'm looking for the opposite of this right triangle here. So I can use sine to do that. So I can say that the sine of 60 is equal to H over 10. And so H is equal to 10 sine 60. Now 60 is on the unit circle. So we know that the sine of 60 is equal to square root of 3 over 2, which will give me 5 square root of 3. That's not super helpful when I'm trying to compare it to this 9 over here. So what I'll do is I'll go back to Desmos and I'll go 5. And I see that I have 8.660. And so I have a situation where H is less than little a, which is less than, in this case, C, but we usually call it little b there. So this is a two-case scenario. All right, so I am going to first try and solve this for the first possible case, which would be this case right here. So we'll go case 1. And for case 1, we'll go angle A, angle B, angle C, little b, little c. And again, we know some of these values. We know that A is 60, little a is 9, and little c is 10. So A is 60, little a is 9, and little c is 10. So we just got to find the remaining values. And we do notice that the 60-degree angle and the side opposite A is 9. And I should differentiate so you can tell the difference, my A and my 9. And so the first thing that we're going to try and solve for is this value C right here. And so what we'll do is we will set up that proportion involving the A's and the C's, and we'll say that the sine of 60 degrees over 9 is equal to the sine of C over 10. Now this is a little bit different than the last example, because in the last example the variable was one of the lengths of the sides, not an angle. But we will solve it in a similar method. To get C by itself, the first thing that we're going to do is we are going to multiply both sides by 10. So if I multiply both sides by 10, I will have the sine of C is equal to 10 times the sine of 60 degrees over 9. And then to get the C by itself, get rid of the sine, I'm going to take the arc sine of both sides. So I'll have C by itself, and I'll have the arc sine of 10 times the sine of 60 degrees over 9. And this we will just enter into Desmos. That'll give us the measure of angle C. So we will go arc sine, and we'll put two parentheses, one for the entire sine and then one for the numerator. We'll go 10 sine 60. We'll close the top. We'll go divided by, and then we'll have 9 on the bottom. That'll leave us with 74.207 degrees. 74.207 degrees. So come on up here. 74.207. And so now I have to solve for angle B and little b. And what I want to do here is I'm going to unfortunately have to use a derived answer. And again, we're going to use the triangle sum theorem and say that the sum of these three angles have to be 180 degrees. 74.207 plus the 60 degrees plus angle B has to equal 180 degrees. And so let's just subtract both of those from 180 and get angle B by itself. And we can do that in Desmos. And so if I go back to here to Desmos, let's make this right here go A equals. And then what we can do is now I can use all of those decimal places, and we'll just go 180 minus the 60. That's the angle that was given to us minus A, which is this value here. And so I'll have 45.793 degrees. That is my angle B. So 45.793 degrees. That'll give us that value. And then solve for B as our final value here. What we'll do is we'll use the given information and these two values to figure out what little b is. So we'll go the sine of 60 degrees over 9 will be equal to the sine of 45.793 degrees over little b. And we will cross multiply and divide, which will give us b is equal to 9 times the sine of 45.793 degrees over the sine of 60 degrees. And we'll go to Desmos to do that. And again, I'd like to use all of these values again. So I'm just going to put it in as a b equals. That'll give me all of these decimal values. And I can rewrite this as 9 times the sine of little b. And I want that whole thing in parentheses. So let's put some parentheses around this. And then we'll go divided by the sine of 60. And I get 7.449 for that one. All right, so I have all of the values that I need for case 1. Now, case 2. All right, for case 2, I start with the same values. I still say that angle A is 60 degrees. I still say that little a is 9 units long. I still don't know what angle B is. I still don't know what angle C is. But I do know that little c is 10. Now, in the first one, I solved for angle C first. And again, it's fairly simple to find that C for the second case. All right, if you think about it, I need the corresponding value in the second quadrant to this 74 degree angle, 0.207. I need this value right here. And finding that is actually pretty easy. I'm just going to subtract that from 180 degrees. So the measure of angle C for case 2 will just be 180 minus angle C, and this will be from case 1. And so I'll go 180 degrees minus 74.207 degrees. That'll give me, let's do that in decimals here real quick. And there's my A, so we'll just go 180 minus A gives me 105.793. Now, just like in the last one, I'll use the triangle sum theorem to calculate angle B here. And so we'll just subtract these two values from 180 degrees. So we'll say angle B is equal to 180 minus 60 minus 105.793. And I will set that equal to C there. And so I'll go 180 minus this given 60 minus C, and it's 14.207. I'll have to round that up. And then it's a very simple matter to solve for this last B. We will again use the law of sines. I know that the sine of 60 degrees over 9, that's the ratio between A, is equal to the sine of the angle that we just calculated, 14.297 all over little b, which we have to calculate. Cross multiply and divide, I get b is equal to 9 times the sine of 14.297 all over the sine of 60. And I'm just going to put that into decimals, and we'll finish this one up. And just for the sake of argument, we'll call this angle D, which we're going to put in there. So the parenthesis for the top, 9 sine D, close that parenthesis, divided by the sine of 60, gives me 2.5505. So I'm going to round that up to 2.551. And now I have all of the solutions for both cases. I know that was a lot, but we got her done. All right, next example. In this next example, we are going to use a novel method to find the area of a triangle. Now, you already know that the area of a triangle is 1/2 base times the height. So if I know the base, I know the height, I can go 1/2 times this base value times that height value gives me the area. But if we look at this, and I am given two sides and an included angle, so side, angle, side, I think that we can come up with a very easy method to solve for the area of a triangle. Now, as I said in an earlier example, the height is perpendicular to one of the bases. So that forms a new right triangle, and I can calculate the height based on this side here. If you can see this triangle, you can say that the sine of theta is equal to h over a, which means that h is equal to a times the sine of theta. I'm just cross multiplying. Multiply both sides by a. What I can do is take this original formula for area and replace the h with this expression right here. So that would give me a is equal to 1/2 that base times a times the sine of theta. So a new formula, if we'll just reorder to keep it in alphabetical order, a is equal to 1/2 a times b times the sine of theta if theta is the included angle between A and B. So we have a new method for finding areas of triangles. Let's do an example. If I label this triangle as A, B, and C, this side here becomes little a, this side here becomes little c, this side here becomes little b. Angle B is 130 degrees, little a is 92, little c is 30. I have my two sides in an included angle, so I can say that A equals 1/2 AB sine theta, and in this case, my A is 92, my C, or B in this case, is 30, and then my theta is 130 degrees. There is no unknown on the right-hand side, so this just became a plug and chug. We can go to Desmos and calculate that. And so we'll just go 0.5, there's my half, times 92 times 30 times the sine of 130, and we get 1057.141 units squared. So 1057.141 units squared. And yes, you do need units squared because this is area and not just a length. All right, that's all I got for today, folks. So, the Star Wars fun fact of the day: in her 2016 memoir, Carrie Fisher revealed that during the filming of A New Hope back in 1974, she and Harrison Ford had an affair. At the time, she was only 19 and Mr. Ford was 33 and he was married. Ooh, drama. Well, that is all I've got for today, folks. You have a great day. Goodbye.